Hello, and welcome to Neuroville's first hosted webinar. We are thrilled for having you here today. My name is Mohammad Naji, and I'm the founder and CEO of Neuroville. I'm your host today, and I will be joined by my colleague, Saber Sisler, to introduce you to a one-of-a-kind evolutionary neurorobotics platform called Fiki. We will start our presentation by outlining the opportunities and the inspirations that led us to propose the solution. We will share details about our implementation and will demonstrate it in action. We'll share platform's availability and its future, and we'll conclude the webinar with a Q&A session so you can ask questions. We have a lot of content, so let's get started. The field of AI and robotics have become tightly coupled, and both have made amazing progress, especially over the past decade. There are robots that can solve Rubik's Cube, backflip, or imitate human impressions. But when it comes to service robots, the kind that can help us in our daily lives, we don't see that many out there. The ones we see come in very limited functionalities. Currently, they are mostly used for floor cleaning, delivery, entertainment, or advertisement. Still, it is inevitable that in close future, they will become an inseparable part of our lives. If you could have thought of smartphones before the introduction of iPhone, we now are at the point with service robots in a similar situation. So why availability of such robots taking so long? Well, it mostly boils down to the lack of functionality, lack of versatility, and safety concerns while addressing them at a reasonable cost in an autonomous form factor. At Neuroville, our mission is to build the needed technologies that can enable robots gain such qualities and become our helping hands. Our ultimate goal is to make a difference in the lives of the most vulnerable members of our society by developing assistive care solutions. Achieving this goal is not going to be easy. If we expect robots to become capable enough to help us when we are in need, they will need to be able to navigate our environment, use our tools, and interact with our infrastructure. Such expectations from robots would be a colossal task and an engineering nightmare. It's no surprise that we still don't have such robots available. So why is it so hard to have functional and usable service robots? The shortcoming in robot control systems is one of the key factors. And the best way to answer this question is to draw some comparisons between digital control systems and the biological brain that has enabled us to do incredible things. On the one hand, digital control systems are fast, predictable, and interpretable. On the other hand, we have the biological brain with unprecedented parallelism in data processing while doing it with negligible power consumption. Meanwhile, capable of fast learning, adapting to situations, and many cognitive capabilities that one can only dream of a robot could do. The good news is that over the past decade, there have been numerous technological advancements that can potentially become game changers in bridging this gap. The amazing work from brain research organizations around the world has gained us like never before insights from the inner working of the biological brain. Event-based sensors are enabling the intake of very large amount of sensory data in an effective manner. And the advancements in neuromorphic computing is getting us closer and closer to having a highly parallel and fast processing units with very efficient footprint. We believe this is a pivotal moment in changing the trajectory of the capabilities of autonomous robots, where the key missing ingredient being a framework and system that can effectively bring it all together. At Neuroville, we took it upon ourselves to tackle this challenge. To achieve our goal, we decided to take a step back and look at how this challenge was addressed in nature. What made humans capable? Of course, it was a lot. Our species has been evolved over millions of years. Our mind and body goes through a developmental process that helps transform a helpless child to become an adult, which takes years to complete. And lastly, numerous lifelong but short-lived experiences throughout our lives transforms our plastic brain to become capable of mastering the control of our body and environment. Even though robots are built and operated differently, we believe for robots to be able to do what we do, they will have to go through a similar set of processes to render them capable. While studying the human brain, one observation is that there's a very tight coupling between human brain, body, and the environment, where capability improvements occur as a result of interactions among the three. The field of neurorobotics is defined around this concept, where robot brain, body, environment interactions are studied together. There are also considerations of lifelong changes that robot could go through that could impact its functionality. One of the most successful and notable neurorobotics platforms is called eBrains by the Human Brain Project, where simulated brain models can become integrated with simulated robot bodies and interact with simulated environments. Technology has come a very long way, and the state-of-the-art in neurorobotics is enabling robot brains, body, and environment to work in unity. Through simulation, one can expose robots to different environments and define experiments to evaluate robot behaviors. Robot-robot and human-robot interactions can be studied, and a trained model of one robot can become the starting point of another one. Yet, we saw an opportunity to advance the field by bringing in the concept of maturity and evolution to the field of neurorobotics. We defined the platform, we defined the framework that not only brings brain, body, and environment together, but also accounts for processes that can assist the brain, body fusion to develop and mature based on environmental constraints, age-driven processes, and evolution. We introduced an artificial genome that can enable both anatomical and physiological aspects of an artificial brain to become evolvable and capable of going through developmental processes. Furthermore, we defined contextual insights from the inner working of the system to become a part of the workflow to help support developmental and evolutionary processes. We called it the Framework for Evolutionary Artificial General Intelligence, and short FIGI. The process in FIGI starts with the creation of a brain-inspired cortical definition encoded as artificial genes in a data structure known as a seed genome. From there, the system develops the artificial brain using a collection of biologically inspired processes that leads to the creation of cortical areas, neurons, and synapses in data structure called connectome. Initially, the brain starts in its immature form, and gradually through maturity-based processes, the brain shapes and reshapes itself to become capable of effective processing the stimuli and control of all its peripheries. The maturity process is an ongoing one and combined with lifelong learning, where the robot learns and adapts to new situations through its lifetime. Brain death concept is introduced to help naturally limit the age of each artificial instance. Performance analysis is the process used to evaluate the overall fitness of the brain, and the value will be stored alongside genome in a database. An ongoing natural selection process uses the genomes from the database and initiates the creation of new generation of the brain. And from there, the cycle continues. We used the concept introduced as FIGI and built a platform around it to provide an easy-to-deploy package with powerful tools for improved manageability and interoperability. FIGI platform is consisted of a core service developed as a Python library representing the brain and all its associated operations. This core service is integrated with other services that in turn provides means to manage, monitor, and facilitate brain-body interactions. Figi core services is consisted of many subcomponents. Neuroembryogenesis unit handles the brain growth and developmental processes such as neurogenesis, synaptogenesis. The peripheral nervous system unit is responsible for translating external stimuli to neuronal spikes through its input processing unit, referred to as IPU. The reverse is also taken care of by this module, where neuronal spikes are translated back to physical or simulated events. This process is handled through the output processing unit, or OPU for short. The neural processing unit handles all matters associated with neuronal activities and synaptic dynamics, such as neuron firing, neuroplasticity, or neurodegeneracy. The training unit provides the needed infrastructure to externally induce conditions that can help train the brain, such as shock administration. And the evolutionary unit drives all matters related to the evolutionary process. Low latency communication is crucial to enable the artificial brain to have real-time reaction to stimuli. Hence, we used high-speed ZMQ messaging library to handle all the sensory and motor signal transfers. Database adapters enables the storage of brain data in the database, and RESTful API has been implemented to handle all the management requests to the artificial brain. Considering the diversity of technologies and platforms in the field of robotics, we found it essential to design the platform in a way to make it easy to build integrations with, while accounting for interoperability with other solutions. As a result, we chose to containerize Figi core services along with all third-party applications used as part of the ecosystem with two objectives. One, to make it easier to deploy across various system architectures, and two, to make the platform extensible and easy to integrate with alternative technologies. We have been very proud of how the system have come together, and we created a short video about it, which I would like to play it for you now. I hope the video has sparked your interest. At this time, I'm going to invite Sabra to take over and share more details about the platform.
Hi, everyone. I'm Sabra, and over the past few months, I've had the pleasure of working as Neuroville's co-op student, and I'm going to get started today by sharing some of our platform highlights. First, we're going to talk about some of our multi-level learning capabilities, followed by some of our brain insight tools. And then we're going to talk about how Figi supports physical and simulated embodiment. So to first talk about multi-level learning capabilities, we're going to discuss how a lot of the power of Figi comes from enabling learning across multiple timescales. We have our evolutionary system, which supports learning across generations. Based off of our gene-based brain definition, where we can define properties of the brain network, such as the neuronal dynamics and synaptic connectivity, this data structure is very conducive to the processes of mutation and crossover, which leads to a natural variation between members of a generation. We can then use this variation allows us to then do fitness evaluation in order to artificially select for behavioral, structural, and functional traits. Next, we have our maturity system, which is the execution of time-dependent processes that can help shape the function and structure of the brain based off of brain age. Some of these processes include synaptogenesis, which is the creation of new synapses, as well as synaptic pruning that occurs to help refine our networks as we age. Additionally, we have motor babbling and other types of developmental processes. Lastly, we have our adult learning system, and this is enabled by spike timing dependent synaptic plasticity. This synaptic plasticity enables us to use long-term potentiation and long-term depression in order to rapidly update and integrate new information about the environment into the artificial brain. Next, we're going to talk about some of our brain insight tools that Figi provides. So the first tool that we offer is the interactive brain visualizer that's designed for users to gain insights into the structure and the function of the artificial brain. The artificial brain consists of multiple components such as cortical areas, voxels, and neurons. In the brain visualizer, the first thing we can see are our cortical areas. Each cortical areas are groups of voxels, and they all have the same neuronal properties. Within the genome, we can actually define the neuronal morphologies and dynamics for the neurons within an individual cortical area. Each cortical area also has a name that's encoded in the genome. This name helps to further the interpretability of the brain visualization. Within each cortical area, we can see that there are one or more voxels. Each of these voxels can be a variety of colors, and the color change is part of what allows us to visualize the activity of the artificial brain. Blue indicates that the voxel is inactive, so none of the neurons within the voxel have reached their threshold potential, while red means that the voxel is active. This means that at least one of the neurons within the voxel is firing. The last color that a voxel can be is green. A green voxel indicates that the user has selected it. Therefore, if the spacebar is pressed, that voxel will subsequently become active. This allows us to activate neurons in the system in order to understand how activation changes the function of the artificial brain. Although our interactive brain visualizer provides an overview of brain activity, Figi also provides an additional brain activity monitoring tool in order to gain deeper insights into the activity of individual neurons. The Brain Activity Monitor allows users to record the postsynaptic potentials and membrane potentials of individual neurons. This time series data can be extremely useful for tuning circuit designs, testing new software changes, and understanding how processes such as maturity and learning impact the artificial brain. On the top panel, we can see our membrane potential monitor. When the value of the membrane potential exceeds a predefined threshold, the neuron will become active, which means that it alters the state of the downstream neurons by temporarily increasing or decreasing the probability of activation. It's important to note that although we incorporate dynamics into our system, such as neuronal inhibition, refractory periods, temporal summation, and neuronal leak, just to name a few, the numbers represented by the system are not intended to replicate the dynamics of biological neurons, but purely to take inspiration from them. On the bottom panel, we can see our postsynaptic potential monitor. This panel, the value of our postsynaptic potentials represents the influence that upstream neurons have on a downstream neuron. Next, we're going to talk about our physical and simulated embodiment capabilities. Figi supports a fully simulated environment that's powered by Gazebo Sim. This is a physics simulator that enables the creation of customized simulated environments that still have real-world physics dynamics. Within the simulated environment, Figi has multiple preset robots that are designed for particular tasks, but users also have the ability to create their own robot embodiment using ROS2 and Gazebo. This allows users to add various types of sensors, including infrared sensors, cameras, or ultrasonic sensors. And it also gives them the ability to modify the shape and the weight, the size, the materials, etc., of the robot body. This customization of robot embodiment is important for two reasons. One, it allows us to model existing hardware. Modeling existing hardware provides a safe alternative for testing new brain designs without risking damage to our physical robots or hardware. Second, it allows us to create and to design new robots. This allows us to explore the capacity of the artificial brains in different bodies. It also allows us to design robots intended to perform very specific tasks and with very specific behaviors. As we know from biology, both the function and the structure of the brain is very tightly coupled to the structure of the body. So the ability to create and design new robots also poses a really promising future direction in our evolutionary platform, because it would potentially give us the ability to co-evolve the brain and the body. Although our simulated embodiment and environment is really important for ease of testing, exploring new embodiments, it doesn't account for how robots behave in the real world. Because although testing robot functionality in physical environments as well is also essential to understanding not just how robot brains function in theory, but how they actually function in reality. Figi currently supports integration with Raspberry Pi and microbit hardware, and that allows us to use Figi in real time with microbit and Raspberry Pi enabled robots. For our next section, I'm going to just do a demo. So we're going to start by introducing the learned line tracking task, followed by an intro to the Figi workflow. And then we're going to walk through some pre-recorded demo videos of the actual line tracking task. So in order to display some of Figi's tools and basic functionalities, we're going to demonstrate a task called learned line tracking. To perform this task, we're going to use the three-wheeled simulated robot that can be seen in the center of the screen. This robot has 3 IR sensors that are evenly distributed on the underside of the front pole. There's one on the center, one on the left, and one on the right, as can be seen by these small red dots here. These infrared sensors allow the robot to detect bright and dark spaces. The reason this task can be considered learned is because initially the robot will only perform a default behavior, which is moving forward. The robot learns to track a line by associating a neutral stimulus, such as driving on a dark or bright surface, with an externally administered aversive stimulus, such as a simulated shock. This means that, for example, if the robot is conditioned to avoid a bright surface and is subsequently placed on a dark line, it will continue moving forward until it starts to deviate from the line, where when a bright surface is detected by one of its IR sensors, it will then perform avoidance behavior, causing it to reorient itself back onto the line. Below, we can see the general architecture of the artificial brain that's performing this task. In blue, on the lower left-hand side, we have our input processing units, or IPUs. The IPUs are used to convert external stimuli, such as infrared activity or simulated shock, into cortical activations. These are analogous to primary sensory afferents in the biological brain. On the lower right-hand side, we can see our motor output processing unit. This converts cortical activations into a format that can be interpreted by the robot's motors. OPUs are similar to how lower motor neurons work in biological systems. Initially, the synaptic weights between the detect dark and detect bright IPUs in blue and their respective avoidance cortical areas, as shown in teal on the upper left-hand side, is not strong enough to activate the avoid dark or bright cortical areas, meaning that the robot will not alter its behavior in response to infrared sensor data. The avoid dark and avoid bright cortical areas are representing this negative valence or association with the detection of either a dark or bright surface. The avoid bright and avoid dark cortical areas are the perception associated with being on one of these surfaces. And so if that negative perception is active, the avoidance behavior will occur. During training, a simulated shock will shock the robot in either a dark or bright space, which can be detected by the shock IPU. The shock IPU, as shown in blue, will activate the avoid bright and the avoid dark association areas in teal on the upper left side, so that the synapses between either the detect dark or detect bright IPU and the corresponding avoidance cortical area will be strengthened until eventually the activation of a single infrared sensor is enough to activate the avoidance behavior, which can cause the robot to turn away from the IR sensor combination it is conditioned to avoid. Now I'm going to introduce the Figi workflow. So first, we must select an environment type. For the purposes of learned line tracking, we're going to select a virtual environment. Next, we have to select our environment design. Figi has multiple presets, but it's super easy for a user to exchange and customize the environment design with their own PNG image. They can also create their own meshes and upload those into Gazebo in order to create a custom topology, such as hills or valleys. For the purposes of learned line tracking, we're going to select the map that has a bright background with a dark line. Next, we need to select a robot. Figi also offers multiple preset robot options where we have the left is a stick bug. This is meant for designing central pattern generators. In the middle, we have our three-wheeled robot that we'll be using for line tracking. And then we also have the capability to test embodiment with a drone. After we select our robot embodiment, we then need to select a genome mode. The first genome mode that Figi offers is our sample genomes. Our sample genomes have multiple preset options that allow a user to get introduced to Figi, that they go along with tutorials, as well as just showing some of the basic capabilities that Figi offers. Users also have the ability to upload their own genome. Users can either modify one of the sample genomes or create their own in a Python file or JSON file and then re-upload that to the application. Lastly, users have the ability to use the autopilot mode. The autopilot mode is a precursor to our evolutionary system. For line tracking, we're going to upload a genome called the conditioned avoidance line tracking genome. Once we load a genome into Figi, we can see two panels. On the right is the robot embodiment and environment simulation, and on the left, we have our interactive brain visualizer. On the left-hand side of the interactive brain visualizer, we can see our sensory-related cortical areas, such as the input processing units that are detecting the bright and dark surfaces using the robot's IR sensors. We can also see our brightness gradient detection cortical areas, as well as the cortical areas associated with the avoidance of a dark or bright surface. On the right-hand side of the interactive brain visualizer, we can see the cortical areas associated with motor actions, such as avoidance and default behavioral action patterns, our motor decision-making cortical areas responsible for the individual motor actions, and we can also see our motor OPU, which is what controls the power designated to each of the robot's motors. As previously mentioned, the default behavior cortical area is consistently active. This cortical area activates the forward region, which in turn is going to activate a combination of motors that result in a forward action. On the right-hand side of the screen, in the simulated environment, we can actually see that regardless of what surface the robot is on, it's continuing to move in a straight line, and it's continuing to move forward regardless of the infrared sensor combination that's active. Before we proceed, I want to draw our attention to our initialized position OPU. This OPU is a special cortical area for training and convenience purposes that, when activated, will move the robot to a preset location on the map. By selecting a voxel and pressing the space key, we can move the robot to a preset location in order to help assist with training. The right side of the map was strategically designed to repeatedly expose the robot to both bright and dark conditions. So now when we activate the initialized position OPU, we can see that it is moved to the right side of the map. Next, we're going to enable the shock scenario. There are two currently available shock scenarios, which are a dark surface shock and a bright surface shock. Currently, I will select this bright surface shock. This shock scenario will administer a shock when all three of the robot's IR sensors are detecting a bright surface. So now we can see that as the robot drives over a bright line, we can see that all three of the robots detect bright voxels are active. And then as it drives over a dark surface, we can see that all three of the detect dark voxels are active. Additionally, we can see that when the detect bright cortical area is active, that the shock IPU is also active. The shock cortical area activates our avoidance cortical areas which then increases the LTP or the long-term potentiation between the active infrared sensors, such as the detect dark or detect bright cortical area and the respective avoidance cortical area, so that eventually the activation of any single voxel of the darkness or brightness detection cortical areas will be sufficient to activate the respective avoidance area. This in turn leads to a steering away from the bright space and allows the robot to go back onto the dark line. As training starts to wrap up, we need to first disable the shock. Then we're going to use our initialized cortical area to move the robot back to the line, where it should now be capable of line tracking. As the robot starts to progress along the line, we can see that once one of the IR sensors detects a bright surface, we then see an avoid bright cortical area active, activating avoidance behavior, leading to motor decisions, and a right motor action, leading to a robot turning right in order for it to reorient itself back to the dark line. To better understand some of the cortical dynamics that lead to our desired line tracking behavior, we can use our brain activity monitor. By clicking on the brain activity monitoring icon in the top of the screen, we can go to the brain activity monitoring page. On this page, we can see our membrane potential monitor in the top panel and our postsynaptic potential monitor in the bottom panel. In this situation, we are looking at the membrane potentials of the avoid bright cortical area, and we are monitoring the postsynaptic potentials of all of the neurons that are synapsing onto the avoid bright cortical area. It's important to monitor these postsynaptic potentials because they're it's important to monitor the postsynaptic potentials that are influencing the avoid bright cortical area because we want to understand how the upstream neurons are contributing to the activation of avoidance behavior. The upstream neurons of the avoid bright cortical area are the shock IPU, as seen in orange, and the neurons from the detect bright IPU, as seen in blue, green, and yellow. The detect bright IPU has 3 neurons, and when active, each neuron represents that either the left, right, or center IR sensor infrared sensor is detecting a bright surface. Because the activation of the shock IPU only occurs during training, the presence of the orange line in the bottom panel indicates that training is in progress. This means that eventually the strength of the synapses between the neurons and in the detect bright cortical area and the avoid bright cortical area will be strong enough to activate avoidance behavior after training is complete. Now we can use the brain activity monitor to filter the time window of the data, allowing us to get a closer look at the impact of plasticity during training. Here we can see that the value of the postsynaptic potential for the shock IPU, as seen in orange, doesn't change during training. This is because plasticity is not enabled for this synapse. In contrast, we can see that the value of the postsynaptic potentials between the neurons in the brightness detection IPU and the avoid bright cortical area are increasing during training. This is due to our spike timing dependent long-term potentiation. Now, the brain activity monitor provides an easy way for us to visualize some of the neuronal dynamics within the artificial brain. So now, when we return back to line tracking, we can see here that the robot has continued to track the line. And so even though this robot is slow, we can appreciate that part of the importance of the learned line tracking task is that its capacity for the robot to actually learn to track both a dark and a bright line. Here we can see a sped up version of the robot undergoing the same paradigm we just watched, but now we can see it tracking both a dark and a bright line. Although learned line tracking is a relatively simple task, we're demonstrating Figis as an end-to-end solution. This task allows us to see how training and life experience, as well as and how the synaptic plasticity provided by our artificial brain leads to a change in behavior. Additionally, the learned line tracking task displays how, when coupled with the artificial brain, the customized embodiment and the simulated environment can all contribute to the resulting robot behavior. Now I'm going to pass it back to Mohammed.
Thank you, Sabra. As demonstrated, a brain-inspired circuit implemented in Figi was capable of learning the line tracking task. We've shown that the same circuit with minimal conditioning can adapt to a completely different circumstance and perform line tracking in an opposite color track. In this example, we did not use any of Figi's evolutionary capabilities, but a simple circuit with only 79 neurons was capable of an amazing performance with minimal conditioning. We, of course, only had very limited time to show you a glimpse of Figi features and capabilities, but there's much more to it. Here, we have summarized them for you. I'm happy to announce that everything demonstrated today, as well as everything listed here, is available for download today as beta software. We have licensed Figi under Apache 2, and we are releasing it for free. Our goal is to enable Figi to become the most popular platform for developing control systems for service robots and virtual avatars. The concept behind Figi is multidisciplinary, bringing the fields of robotics, neuroscience, and computer science together. It also brings together many technologies to be able to do the needed capabilities. If you have skills in any of these areas, we are inviting you to join Figi's open source community to help Figi grow to its fullest potential. Neuroville is heavily invested in Figi's success as an open source platform, and we welcome any joint research or commercial collaboration. We can also provide assistance in having Figi integrated into your workflow or existing platform if you're interested. What we have shown in this webinar is just the beginning of a very long journey ahead of us. Artificial general intelligence has tremendous potential in developing solutions that can help improve lives. And our goal is to continue to develop technologies that can help it to become a reality. We will continue to improve Figi as a platform and plan on adding additional physics simulators. We plan to develop and put efforts into design of functional circuits for controlling robots. We plan to pilot integration of neuromorphic technology into Figi. And given the value we see in accessibility and usability of Figi, we plan to release a hosted version of Figi as a service by early next year. Based on popular demand, we will also host technical webinars. So please let us know what you'd like to learn more about, and we'll plan for that. I'm happy to share that we are hiring and would love to have talented people like you joining our team. If you're interested, please send us your resume. Last but not least, I would like to thank our amazing team for their incredible work that helped us get this far. It would have not been possible without their talents. I would like to thank you for your time and attending this webinar.